In problem 8, we return to the situation of problem 2 where we have a layer of mass m and an instant later an exiting mass m down here. We're asked to use the energy considerations, and then that's what we do over here, and then Bernoulli's equation to show to determine what the velocity of the exiting water is. Now, of course, in the problem you're given numbers, but here we're going to do everything with symbols. So we say that as the mass m goes from here down to here, the potential energy change is negative mgh. Now we saw that, I believe it was problem 2, you might want to review that. Since we're assuming there's no dissipation of energy, then the change in kinetic energy is plus mgh. Okay, again, now the system loses mass m up here, gains mass m down here. Potential energy then thereby decreases, the kinetic energy increases by the same amount. Since the initial velocity up here is very close to 0, by assumption this is a large container, the container is large compared with the whole, the exiting velocity has a property that 1/2 mv squared equals mgh. That is, the exiting kinetic energy equals the change in the kinetic energy. Then we solve for velocity and we get square root of 2gh. This is just the same as our previous treatment of the problem. What does Bernoulli tell us? Well, if we look at it from Bernoulli's point of view, we have atmospheric pressure here, we have atmospheric pressure down here. So the pressure is 1 atmosphere both at the top and at the exit, so that the pressure is constant. Since the pressure is constant, we're going to conclude that 1/2 rho g y is constant. Now I'm going to use y instead of h for the altitude. We can really use any symbol we want here, but h is going to stand for this specific altitude. So that the 1/2 rho v squared plus rho g y is constant. Now y changes from h here to 0 here. So that at the top the velocity is 0 and the y is equal to h. So we have the 1/2 rho v squared plus rho g y is 1/2 rho times 0 squared plus rho gh. Again, velocity is 0, altitude is h. Down here, the velocity is unknown and the altitude is presumably, well, we've determined that the altitude here is 0. We've declared that this is our 0 point for altitude. So that 1/2 rho times v exit squared plus rho g times 0 is this side, and these two have to be equal. Okay, at the top, the 1/2 rho v squared plus rho gy has to be equal to the 1/2 v exit squared plus rho g times 0. This term's then 0 and this term is 0. We're left with the 1/2 rho v exit squared equal to the rho gh. And we easily solve for the v exit. We get the square root of 2gh. So that gives us our exit velocity, which of course is consistent with this velocity. So Bernoulli's equation in this situation expresses energy conservation.